Okay, so linear combinations of oscillations. We're going to start off with just simple harmonic motion. Okay, so this is, I'm just sort of sketching things out here. So simple harmonic motion, you have a wall, and you have a spring, and you have a mass attached to it, right? You count this as 0 here, right? And it's on a frictionless surface, okay? So y, you know, as time moves, so you pull the mass, and the spring pulls back on it, or you push the mass, and the spring pushes back on it, right? And so we use y to denote the displacement, so positive in this direction, negative in this direction, right? So depending on you know, y is the displacement at time t, right? And there's a physical law called Hooke's law, right? Hooke's law that says that the force of the spring is proportional to the displacement, right? The force of the spring is proportional to this displacement. So that is, the farther you pull it away, the greater the force, and that force that is related in a linear manner, right? So the more you push it in, the greater the force, right? So that is, force is equal to some constant times the displacement. The force, the restoring force, F, is some constant times the displacement. And people like to think of this constant as positive, so it's written as negative k, because the force will be opposing the pull, right? So like if y is positive, then the force is going to be negative, right? So that's why if you're thinking of k as, if you want to think of k as positive, so this thing is called the spring constant. One likes to think of the spring constant as positive, so in the equation you write, you know, force is equal to negative k times the displacement, right? Okay. Then you know, force equals mass times acceleration, so you get the mass times the acceleration equals negative kyt, right? And so this gives you that. This gives you y double prime plus k over m yt equals 0. Okay. So this is the differential equation that the displacement is going to satisfy for the spring. Okay. Okay. So one denotes this as this constant as c squared, this k over m, and then it's a homework problem for you that the general solution of this equation is y has to be some linear combination of sines and cosines. You know, a cosine ct plus b cosine ct. Okay. So one way is easy, to see that these are solutions is easy. To see that these are the only solutions takes a little bit more work. So these are the only solutions, assuming that y is twice differentiable. It's 2 times differentiable. Okay, so that's just, you know, where things start, and that's this seems kind of disconnected at this point, but we'll connect it into what we're doing. So for those who came in late, what we're talking about today is basically you know, how Fourier series arise in nature. Okay. So okay, so yeah, so there'll be two things, either one or two things that we talk about. One is called the wave equation, and the other is called a heat equation. I'm not sure we'll get to the heat equation, but okay. So okay, so here's the setting. You have a string that is bound at both ends. It's fixed at both ends. Okay, and you set it up in some initial position. You set it up in some initial position, and then you let it go. Okay, and you want to know how the string, how the string moves through time. Okay, like how does that depend on the initial position, et cetera, et cetera. Okay, so you have a string. It's of length L. You let uxt denote the displacement, the vertical displacement, right? So this is x, right? This is x, and uxt is at the vertical displacement at position x and time t, right? So if we have ux0, that would be, if we look at ux0, that's going to be the position of the string at time 0, right? So just you can think of this initial position as the graph of ux0, right? And then as time goes on, the displacements are going to change. Okay, so the wave equation. So I'm not going to do this part, but physical considerations imply that if U is 2 times differentiable, then it has to satisfy something called the wave equation. That is, the partial of U, the second partial with respect to U, 1 over c squared times the second partial of U with respect to time equals the second partial of U with respect to x for some constant c. Okay, so this thing is called the wave equation. Okay. Okay. Okay, so the first thing we're going to do is we're going to simplify the equation by scaling the coordinates. Okay, so we'll do, we basically want to get rid of this 1 over c squared, and we also want to scale the string so that it's of length pi. Okay, so we'll do some rescaling. So basically, we'll, without loss of generality, we can assume that the length is pi, and that we're dealing with that c is 1. So why is that possible? So we're just going to rescale. We're going to rescale the units. Okay. So the first thing we do is we say, well, look, right now x is ranging between 0 and L. So that's the same thing as saying that x over a ranges from 0 to L over a. And so what we do is we let capital X be this x over a, and let A be L over pi. Right. So that then in that case, capital X is ranging from 0 to pi. So that's one change we'll make. Okay. Yeah. So capital X is going to range from 0 to pi. And then the second thing to notice about that change is that if you're taking the partial with respect to capital X, well, that's the same thing as taking the partial with respect to little x, and then the partial of x with respect to capital X, right? Just by the chain rule, right? Okay, chain rule. And so you get this. You get a. Oh, this is. You're laughing because how can you tell the difference between the little x and the big X, right? I think that's why you're laughing.
That's exactly why I'm laughing.
Yes. Okay, let me make the big X's bigger. Okay. This is. I think I mentioned last semester the one off ridiculed professor at University of Chicago who is said to use only two variables, alpha, but rotated 45 degrees. Counterclockwise, and then gamma, but rotated 45 degrees clockwise. Right. Yeah. I am now Professor Rothenberg. Okay. I hope this is. I guess this makes it easier for me because then anyway, you get this. Okay. Right. So that's one thing. The second thing we do. The second thing we do is we let t be t over b. Okay, and then similarly, right? When you differentiate with respect to capital T, well, you're going to get b times the partial with respect to little t. Again, by the chain rule. Okay, and so what's the point that then when you differentiate twice with respect to t, well, you get 1 over b squared, the second partial with respect to capital T, right? Similarly over here, same thing over here, right? And so so this equation, right? So this 1 over c squared, this thing, right, turns into 1 over c squared b squared d capital T, right, equals 1 over a squared d squared d capital X squared. Okay, so yeah, so, well, let me write it this way. So letting u of capital Xt be little u of little x and little t, you get this. You get this equation. But then, if you let b be L over c pi, and a be L over pi, then these constants cancel out. Okay, and so you end up with d squared u dt squared equals d squared u over dx squared. And like we said before, x ranges from 0 to pi. Okay. So all that was just to say that we don't have to deal with the c. Okay. So we can assume that c is 1, and we can assume that the length of the string is pi. Anyway, so it's just rescaling. So without loss of generality, by rescaling, we can make these assumptions. Okay, that's just, yeah, that's not that interesting. Okay, so in any case, we have this simple form of the wave equation, this reduced form of the wave equation, and the first thing we're going to do is think about the wave equation on the entire line, rather than on just on that fixed string. Okay, so let me just keep it. Okay, so the wave equation on the real line. Okay. So we're going to solve this in two different ways. We're going to think about this in two different ways. The first way is not directly related to Fourier series. So the first way is due to D'Alembert. And this is the method of so-called traveling waves. And then the second method will be doing basically like a separation of variables. And that one will actually more directly motivate Fourier series. But this first method of D'Alembert we're going to see again later. Okay, when we talk about the wave equation in RD. Okay, so yeah, we should look at it. Okay. So we start off with this. We say so first notice. So we're going to do D'Alembert's method first. Okay. So first. We say, well, first note that if f is twice differentiable, then if we let u of xt be f of x plus t, then, or u of t be f of x minus t, then u solves the wave equation on R. Okay, right? All you need is that that the second derivative with respect to time equals the second derivative with respect to position, right? And when you differentiate that, you're going to get the same thing when you differentiate twice with respect to time or twice with respect to position, right? Here, same thing. The minus signs will cancel out. Okay, so so the point here is that these are possible solutions, right? These are possible solutions. These are so-called traveling waves. Traveling waves, because at time 0, right? When t equals 0, right? U of x0 is just going to be f of x, right? So you have some initial thing, right? And then let's look at the second one, right? U of xt is f of x minus t. So that's just a translate, right? That's just a translation of your graph to the right. So as time moves, this whole thing is just moving in a constant, just moving to the right. Okay, right. And then this one would be moving to the left. Okay, right, as time goes on. Yeah?
Does that imply that given a starting position, we can pick any continuation as long as it's twice differentiable and that's a solution to our wave equation? Or is it?
Yeah.
Okay.
Yeah. Yeah, so this is not the interesting part. Right?
Okay.
This is just an observation that these traveling waves satisfy the wave equation. The interesting thing is that, in fact, well, there are a lot of interesting things, but one interesting thing is that, in fact, claim any twice-differentiable solution U to the wave equation must be a combination of traveling waves. May I make it more impressive? It must be a sum of traveling waves in the opposite direction. Okay. So, right, these guys are solutions, right? These guys are solutions, and if you add them together, you get a, if you have one wave going in one direction, and you have another wave going in the opposite direction, that's going to be a solution, right? In fact, any linear combination is still going to be a solution. And what this is saying is that, whatever solution you get can be realized as a combination of two waves in opposing directions. Okay, and this is just another sort of chain rule exercise. So here's the proof. Okay, so right, say that U of xt is a solution. Okay. And we're going to change variables. Let c be x plus t, let eta be x minus t. Okay. So, x, of course, is going to be x is going to be 1/2 c plus eta, right? And then t is going to be 1/2 c minus eta. Right. Denote v of c eta as u of xt. Okay, so then again by the chain rule, well, if we differentiate with respect to c, right, that's the same thing as differentiating with respect to x, and differentiating x with respect to c, and then also plus differentiating with respect to t, and differentiating t with respect to c, right? But dx dxc is a half, right? dt dxc is a half, right? And so you just get 1/2 ddx plus ddt, right? So return to Calc 3. Right. Similarly, ddxc is 1/2 ddx minus ddt. And so so if we consider the second partial of v with respect to c and eta, Well, that's going to be, this followed by this followed, this followed by this, right? And so what you end up with is 1/4, d squared, over dx squared minus d squared over dt squared. Right? Because you're going to get some mixed partials, but the mixed partials, you can switch the order of the mixed partials, right? And then, and so you get 0, right? The mixed partials can be switched because of the twice differentiability. Okay, so you do need twice differentiable. So there's something called Clairaut's theorem about when it's okay to switch the order of mixed partials. Okay, so this is 0, right? Okay, so what do you see? That this is going to be 0, right? And so when you integrate it, right? First you integrate with respect to eta and then to xi, or in either direction. In either case, what you end up with is that v of xi eta is some function of eta plus some function of xi. Sorry, I said it backwards. Right. Right. When you integrate this thing, you're going to get some constant. When you integrate with respect to eta, say, then you get some constant, but that constant depends on xi. Then you integrate with respect to xi, and you get something that depends. You get the integral of that constant that depended on xi. So that gives you a function of xi, right? And then you get some constant that depends on eta. So you get this. And so what you get in the end is that you get f of xi, some function of xi plus some function of eta, right? In other words, your solution was a combination of waves in opposite directions. Okay, so this is just this is just the chain rule basically. So if you have a solution, then it must be a combination of waves in opposite directions. Okay, so is that okay? Everybody all right with that? Okay, great. Okay. So now we want to go back to the thing that we were interested in the first place, which was the string that is fixed, fixed. So here's 0 and here's pi. The string that is fixed at the endpoints, right? So the values are 0 here and here. Okay. So what we do is we take that and we extend it to the entire. We extend it to the entire plane, entire line. So what you do is you say, well, I'm going to, I started off. So maybe you have some initial position. What you do is you extend it. You extend it as an odd function. You extend it as an odd function to negative pi pi. That's the first thing you do. And then the second thing you do is you take the periodic extension of it. So you take whatever it is, and then you just repeat it, right? You repeat it, right? So you just repeat it throughout the entire line. Okay. So starting off with, returning to 0 pi. So if you have some solution, if this is a solution on 0 pi, we extend it to the entire line as above. Okay, by extending it in an odd manner first, and then extending it periodically to the entire line. Okay. So now, right, then, by what we just saw, this must be a combination of waves in opposite directions. It must be some function g of x, f of x plus t, plus some function g of x minus t. Okay. So so what are f and g? Okay, so let's see. Yeah, so if f of x is u of x0, so this is the initial position of the string, right? Well, we know that that's going to be f of x, capital F of x plus g of x, right? Okay, so that's one thing that we know. It turns out that we need to impose another to determine f and g uniquely, we need to impose another condition that is like a sort of initial velocity condition. Right, so what we have here is we have some sort of initial position condition, right? We're saying that these guys have to be this at time 0, but we also need to impose a velocity condition in order to identify f and g uniquely. So so here's the condition that du dt at time 0 is some function g of x. So we have another, right, here's part of our boundary condition, here's another part of our boundary condition, right? This is the position, and then this is the initial velocity condition, okay. Where, so again, g is an odd 2 pi periodic function with g of 0 and g of pi being 0. Okay, and once you put this condition on, then that's enough to figure to determine what u must be exactly. Okay, so we have we have that f of x plus g of x is little f of x. We have f prime of x minus g prime of x equals g of x. right? From here, right? You right, when you take the you're taking from here and here, right? Yeah,
Yeah.
right. Everybody see that? I hope. Right. Okay. So those two together together give you that. Right, if we differentiate the first guy and add it to the second guy, we get 2f prime x equals f prime x plus g of x. Right. If we differentiate the first guy and subtract the second guy, we get 2g prime x equals f prime x minus g of x. Right. So just playing with these two things, we get this. Right. So then just using the fundamental theorem of calculus, you see that f of x has to be 1/2 of f of x plus some antiderivative of g, plus some constant. Same thing for g. That g of x is going to be 1/2 of f minus antiderivative plus some constant. Right? And so, right, so what's u? U is going to be the sum of those guys, right? So it's going to be 1/2 of, I'm sorry, it's going to be the sum of those guys evaluated at x plus t, right? So you get x plus t and x minus t, excuse me, right? So you get 1/2 f of x plus t plus little f of x minus t plus 1/2 the integral of little g from x minus t to x plus t. Right, plus the constants, C0 and C1, but, I'm sorry, plus C1 and C2, sorry. But the sum of those guys is 0. But C1 plus C2 equals 0 because f of 0 plus g of 0 f of 0 plus g of 0 is going to be little f of 0, right? It's going to be little f of 0, which is 0, right? And from here you see that, so that, what does that tell you? That tells you that C1 plus C2 is 0. Yes? Does that make sense? Kind of.
Why is little f of 0, 0?
Because remember, little f, the thing was fixed at the endpoints.
Oh, okay.
So, yeah. Yeah.
And are we just imposing the condition that g at 0 and g at pi is 0?
Yeah. 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 That's in order to make it continuous. Yeah. When you extend it periodically. Okay. Okay. So so this vanishes. The constant, the sum of the constants, the sum vanishes. Okay. So, right. So what's the point here? That we started off with a function that satisfied the wave equation, and that had its sort of initial state, right? This F describes its initial position at time 0, right? And then G describes this initial velocity at time 0. If you know those two things, and you know that this is a solution, then you know exactly what the solution looks like. The solution is going to be a combination of these two opposing waves plus this thing. Okay. So this is D'Alembert's solution for the wave equation on the interval 0 pi. Okay. Any questions? Okay, so that's one way of thinking about the problem, and then there's a second way, which leads to Fourier series. Okay. And so method 2 is called superposition of standing waves. Okay. So what they mean by standing waves are things that look like some some function of t times some other function of x. Okay, so that is 0 is pi, right? So at time 0, you have your sort of initial state, phi of x. Okay, and then I guess assuming that this c is 1 at time 0. Okay, and then this is some sort of like so the initial state of your wave, and then you have what they call an amplifying factor, right? So as time goes on, then these things get multiplied by the amplifying factor. So you have your initial state, and then it just everything gets scaled depending on the factor, right? So that factor is constant for each point in time, right? At every point in time, you multiply it by a different number. It gets all stretched, or it gets all shrunk, or whatever. It gets flipped over, whatever. Okay. So this is amplifying factor. So this is called the standing wave. Okay. So so again, we have our wave equation. Second partial with respect to t equals the second partial with respect to x. We'll have the wave equation. We'll have the initial condition, u of x naught is specified, right? So there's some initial position. There's this initial position condition, and then there's the velocity condition. The initial velocity condition. Okay, so you have this partial differential equation with boundary conditions. Okay. Right. This is the partial differential equation, and these are the initial conditions. Okay, and so I guess we're not going to do it. We're not gonna do it right now, but what we're going to do is to consider solutions that are standing waves. Okay, that is, we'll assume that u of xt, is some function of x times some function of t. Okay, and what that will do is allow us to play the trick of separation of variables. So we'll do separation of variables. And that will change the partial differential equation into a system of ordinary differential equations. That will be easier to deal with, and then we'll solve those guys. And then in the end, we're going to take linear combinations of those guys. Yeah, and that's where the Fourier series will show up. Yeah, Kai.